Hey guys, welcome back. In the last video, we looked at different approaches to store data on disk from a database perspective, and we saw what are the pros and cons, right? To reiterate, there are two approaches, essentially storing key value pairs in a single file or storing each key value in its own file. And we saw what are the advantages and what are the disadvantages. To summarize, when you store key value pairs in a single file, inserts are often because you just add one row onto the file, which is pretty fast. But search is O of n because you need to search line by line and you need to see where your key is, right? But when it comes to an approach where you're storing each key value in its own file, although from a time complexity perspective, it looks like inserts are O of 1 and search is O of 1, there's a lot of disk IO that's being done, much more than the file-based approach, right? Which essentially makes things slower. If all of this sounds foreign, go back to my previous video. I'll link the video somewhere here and we have discussed this in depth. All right. So now we understood that this approach, the approach of storing one key value per file is not really scalable. So when that's the case, what do? We have to somehow make this approach where we store multiple key values in a single file scalable, right? We have to reduce this search complexity of O of n. Okay. So how do we do that? Before we come there, let's kind of quickly go through a sample insert update scenario and see how a file would be after a series of inserts and updates, right? So let's say we insert K1V1, we add K1V1 to the file. Then we want to insert K2V2, it's added to the file. We want to insert K3V3, it's inserted to the file. Now, when we want to update the value of K1 to V4, we don't come here and update the value to V4. Rather, we add a new line saying now K1 is V4. Okay. Why this is and what are the benefits of this is something we'll look at pretty soon. Okay. And similarly, when you want to update the value of K2 to V5, you add a new line. You don't go and update the file, right? So for any inserts or updates, you essentially add a new line onto the file. Okay. So now if we think about this, what is the simplest way we can essentially given a key, find the value pretty quickly? Okay. When we think about our data structures, one thing that comes to mind very quickly is a hash map because hash maps are very famous for O of 1 insertions and O of 1 search, right? Finding a key. So how can we use hash map here to essentially find the value given a key, correct? So that's where the index for today comes, which is called hash index. Okay. So if you actually see how things are on the file, okay, this is a sample representation of how things are stored on file. Although you store data line by line, okay, from if you convert that to bytes, right, individual bytes, it's just separated by a slash n character. Okay, so if you see here, there's a key 1 2 3 4 5 6 and a value which is a JSON object with name with attractions, right, and it's separated by a new line. So until from index 0 till this index 62, right, this is one key value pair separated by a new line. Then the second key value pair starts. Now the second key is 42. The key and values are separated by a comma here, and again there's an object. Okay. So now what we can do is we can essentially say for key 1 2 3 4 5 6, the byte offset in this particular file is 0. So if you open the file and if you look at the 0th index when you convert the file contents into a byte array, the index to find the key 1 2 3 4 5 6 will be 0. You can now for 42 similarly, the byte offset will be 64. You're essentially given a file. You're saying this key can be found at this particular byte offset, right? Byte offset is nothing complex. You have a file. You just imagining that file as an array of bytes, right? As simple as that, right? When it's an array of bytes, you're saying at index when you look at the index 0, that is where you will find the key 1 2 3 4 5 6. When you look at index 64, that is where you will find the key 42 and so on. Okay. So now this becomes your in-memory hash map. Essentially now given a key, you don't have to go through each and every line. You can just come to a hash map. You can see, okay, for now I want to get the value for key 42. I can say that I can see that the byte offset for this particular key is 64. So I don't search, I just straight come to index 64 and I start reading the um, key for 42, right? So that is on a very high level how the in-memory hash map or the hash index works, right? Now let's dive deep in, because this is very high level. Let's go in and let's see what are the nuances here. Yeah. Now we say that key K1 V1, K1 is stored at offset 0. Now K2 V2 is stored at some offset, let's say 22. K3 V3 where K3 starts at some offset, let's say 47, and K4 V4 at 45, right? Now the in-memory hash map or the hash index looks like K1 is, at offset 0, K2 is at offset 22, K3 is at offset 47, K4 is at offset 55, right? So when you store this, when I want to now come and fetch, let's say K3, I know that I have to straight away jump to the 47th index in that file and start reading from there, because I know that this is where my uh, key K3 starts, right? So now this overcomes the complexity of you having to read line by line and figuring out where the key is, correct? Now, when do we update the index? Okay, we update the index when you insert a new key, right? Fair enough. When you want to insert a new key value pair, you essentially add it onto the index. And whenever you want to update an existing key, also you update the index, right? So just a quick example. Let's say before updating, K1 V1 is at offset 0, right? Now let's say, since we're only doing appends on our file, right? Remember, in the actual file that we're storing, we're only doing appends. We're not actually updating the value directly. So what happens is now your offset for K1 changes. So hence you have to update the offset in your index also. You might ask, if we're storing all the data in the hash map itself, why do we even need a file? What happens if your machine goes down? Now your in-memory hash map is stored in memory. It's stored on RAM, correct? And now when it goes down, your data is going to be lost, but you don't want that. That's why you're just storing the index on the memory while you're storing the actual data on the disk, okay? So until now, we saw how inserts and updates work, correct? But when you want to delete, what you would do is you would actually not delete the values, because now let's say a key might have been updated 50 different times, right? Now you have to go and update 50 different indexes. You have to deleting that also causes now problems, because the offsets for each value, each key now changes, right? So you also have to update those, and doing all that during deletion is pretty expensive. So what we do is we just write a special entry on the file saying key 1 has been deleted. Somehow, some marker we keep and say that, okay, when you encounter this, assume that key 1 has been deleted, right? This is called a tombstone, okay? This is a marker for deletion. You might ask one more thing. Why are we storing the hash map in memory? Why don't we store the hash map on disk, so that we won't need to have to one log file like this and one index, right? You can just have one storage and works, right? This is what we saw in the last video. The how do you store a hash map on disk? You store each key as one file, but now that's expensive because you have a lot of disk IO. If you store all key values in a single file, right, now again search becomes O of n, correct? If you store, let's say, all key values in a single file, now search becomes O of n, it's not a hash map anymore. And if you store each file separately, now disk IO increases drastically, which reduces your speed, right? Although it looks like a hash map, the speed is pretty slow. That is why it's pretty hard to implement efficient hash maps on disk. Okay, that is why this index will be stored in memory. Okay, but now since we're storing in memory, there are drawbacks, correct? One such drawback is the data size has to be limited to the RAM size. You can't now increase RAM forever as you increase hard disk, right? Let's say you have a 1 terabyte hard disk, your data gets filled. Now you can pretty much add 1 terabyte of hard disk pretty easily. It's pretty cheap. But imagine the cost of 1 terabyte of RAM, right? That's going to be massive, right? RAM is pretty expensive. So what happens is when you use hash indexes, you have to make sure your keys all fit into the RAM, right? If it doesn't, now the keys that don't fit have to be O of n again, because now you have to again go and search the file. There's no other way. Data is lost after crash. Since the index is stored in memory, if your machine crashes or comes down due to whatever reason, your data is lost because data is stored in RAM and RAM is volatile. Okay. So for the first problem, we really can't do anything, right? This particular index suffers for this problem because we're using RAM specifically. In the upcoming videos, we'll look at different types of index which uses disk. Might not be as efficient, but kind of solves a lot of limitations of the hash index. But the second problem is something that we can solve. How do we do it? It's pretty easy. Let me scroll a bit up. So what we did was we wrote all the key values to a file, right? So this is called an append only log because we kept appending onto the file on every insert, on every update, and on every delete. So what you can do is this file will now be persisted because this is stored on disk. It's not stored on RAM. Even if your machine crashes, when it comes back up, it will have this file. So what you can do is before your database gets ready, you can read this line by line. It's a one-time operation, right? Which is fine. You can read this line by line and you can populate the in-memory hash map, right? This again, this is often you read every line. I agree, but this is a one-time thing. This only happens when your node crashes, which is pretty rare, right? So in those rare conditions, doing one sweep of our data is pretty fine. But doing that for every time you want to get some key value pair is pretty expensive. Correct? I hope that point is clear. Okay. So crash recovery is pretty simple. Correct? We just read the log line by line and we, let's say, refill our hash map. Correct? But there's still one problem. What happens is every time you update or delete or insert, right? You're adding a new line. So let's say now K1 V1 has been updated 10 times. You will actually have 10 entries of K1 V1. Now this is consuming disk space which is not required. That disk space can be used for storing something else, right? This will fill our disk space pretty fast, right? So how do we tackle this issue? Okay, let me come down. Okay. Okay. So one approach is what we do is when a file, right, when the file where we're inserting reaches a certain size, let's say we close that file and we start writing onto a new file. Okay. Now this might be counterintuitive, but just hear me out for a second. This gives us a pretty good benefit that it opens up the possibility of log compaction. Okay. I'll tell you what log compaction is. Let me show you an example. Let me take the case of one file first, then let me take the case of two files. Okay, now let's say we have this one file, right? One segment. So if you see here, you have keys new, pour, and yawn. Okay, I've taken this from a designing data intensive application. If you're interested in these kind of system, read that book. It's a brilliant book. All right. So now new has a value of 1078, right? Pour has 2103, then pour has been updated to 2104, right? Now, when it's updated, a new entry is added. It's not overwriting the older entry, right? So similarly, for each key, there has been updated value. So now if you see, we only have 3 unique keys, meow, pour, and yawn, right? But we have, let's say, 12 different values, correct? Now, this is a lot of wasted space. So what you can do is periodically, once this file closes, right? Once the moment let's say you've been writing to this file, you wrote the latest value mio1082, and now you detected, okay, this file has reached a certain size. I am gonna not write to this file anymore, and I'm gonna write to a new file. The moment you do that, this file is static. This file is not going to change. So what you can do is you can actually compact it. You can run a background job which essentially does the duplication removal for you, right? You can remove duplicates and you can create a new compacted segment. Essentially remove all the duplicate key value pairs and keep the latest pairs, right? And you know which is latest because they would have come in later and they would be on top of your older values, correct? So now you create a new compacted segment, and you can do this asynchronously. You don't have to do it on inserts or during reads. You can, keep serving your reads and writes separately, and this can be done in a background thread. Okay. Let's say now there are two files, okay, and there's duplication across files, right? Because let's say now 1082 was written, but before you could start compaction, you started writing to a new file, and these keys started getting updated again, right? So you create duplicate entries in the second file also. So what you do is you do a compaction and you merge the compacted files. Okay. So once data segment 2 is also ready, you already compacted one till that point. Now you also compact data segment 2, which gives you two smaller compacted files, and then you merge them. Merge is essentially see which what are duplicates here. If there are duplicates, fetch the latest value and put it into one compacted file. Correct? So now two files get reduced to one, and all this duplicate space is now removed, and you have free space on your disk. Right? So compaction and merging. Compaction is essentially taking a file, removing all the duplicates, and creating one compacted file where all the duplicates are removed. Merging is taking two compacted files and then merging them to ensure that all the duplicates have been removed. Correct? So when this is done, you reclaim all the wasted space usage here, and you get a smaller file which you can search for. Okay. So this is essentially a hash index, guys. Whenever a insert or an update or delete comes, you add that onto a file, and you store an in-memory hash map, which is used for lookups. Right now, we all know how in-memory hash maps work and why they're efficient. If you don't know how in-memory hash maps work internally, I'll link a YouTube a playlist by Arpit, which is a brilliant series on how hash map works internally, right? So I link that below. Go take a look at it. So we essentially use the in-memory hash map to make our reads faster. Now with this, our inserts are also O of 1, because you do one insert on the file and one insert in your hash map, and your reads are also O of 1 because you check the offset from your hash map and then directly jump to the offset in the file and read them, right? Of course, when you have multiple files in your hash map, you also store this is the offset in this file, this is the offset in this file, right? And during compaction and merging also, you have to update that because now your offsets have changed, right? Earlier, let's say the latest offset for per was in file to, let's say, some index 300. Now the merged one, let's say they've all merged into file number 1, and this offset is, let's say, 50. So now the offsets in the file has changed, right? You also have to update your in-memory hash map accordingly. Okay. So yeah, when we do all this, we get pretty good reads and writes. Of course, there is caveats. You can't store more keys than what your RAM can contain, right? Otherwise, I mean, if you have more keys, what will happen is you won't be able to store it in the hash map. You'll have to write it on the disk, and then you'll have to again do a O of n search, right? And now that gets tricky because some is in your index, some is not in your index. Whenever something is not in your index, currently, if you restrict to strictly always having on the index, you can be sure that okay, if it's not on your hash map, the key was never written. But if when overflows, you write it onto a disk and don't have space to update it on the hash map. Now for any key which you're searching for, if it's not in the hash map, it might be on the disk or it might not be on the disk. So it defeats the whole purpose of having an in-memory hash map. So whenever you use a hash index, you restrict the usage to the number of keys that can be stored in your memory, right? That's the easiest way to go about it. Okay. Some points to consider, some small nuances which we can kind of look into. What is the file format, right? You can store it in CSV, you can store it in JSON, but since if you see above, we're using, the byte offset, right? Essentially converting the data into binary and then storing the offset of the starting index if we think of it as a byte array, right? So when that's the case, just storing the data in binary would be better, correct? Let me come back here. Yeah. So when that's the case, storing the data in binary is now faster and simpler, right? Because now you know that, okay, my key 123 starts at offset 45 and I have to read till the next new line character, right? Because new line is where a key value pair ends. So you start from 45 and you keep reading byte by byte until you encounter new line character. And the moment you encounter a new line character, you say, okay, this key value pair is read, and you send that value back to the user. Correct? Deletion. We saw deletion. So a new row will be added to the log, right? And now what can happen is during the merging and compaction, you can see, okay, let's say now after this per 2144, let's say mu was deleted. Let's say you kind of create a new entry here. You say del mu, right? Some kind of an indicator to show that mu was deleted. Now, when you merge and compact the segments, you won't include mu in because you know that mu has been deleted, correct? Even when it's not compacted, right? It's not there in your hash map because when you add this entry, you also remove it from the hash map. Uh, okay. Third, let's say when you're writing, you wrote half the data. So you're writing byte by byte, right? Let's say your process was in the middle of writing when your machine crashed. Okay. So what could happen is when your machine comes back up, half of the data for one particular key value would be written, half will not be written, right? How do you detect that? We use something called checksums. Let me show this to you in action. Let me create a file, right? As simple as that. Okay. Now let's say you wanna write the key 123 with a value A, B, C, D, E, for example. Okay. What you do is you have a hash function, okay, some hash function, and you convert this 123, a combination of the key and value. Okay, let's say 123 colon A, B, C, D, E becomes a combination. Okay, let's say now you pass this into a hash function, you get a hash, let's say ZXY, for example. Okay, and again, remember the property of a hash function is that given an input, it always gives you the same output, right? So now what you can do is you can write ZXY and then you write your key value pair. Okay. Now, so what happens with this is, let's say you write the key and in the middle of writing your value, let's say you only write ABC, you were not able to write DE, right? Before writing DE, the machine crashed. Now, what you could do is when you read this line, you get this thing, you again hash it. Okay. If the content of it was same as what you intended to, the hash of this and the hash value here would match. Okay, if it doesn't match, it means something has gone wrong and this data is corrupted and you just ignore this, right? You can do this during crash recovery. So with this hash you can kind of figure out whether this data which is written here you can figure out whether this is complete data or not, right? And if it's complete data, you keep it. If it's not, then you remove it. So in your line, you have a one more hash or checksum, right? So this is how you can handle partially written records. Okay. One caveat here is, and it's a pretty big caveat, range queries take order of n complexity. Okay. Let's say now you want all the key value pairs where the key is between 1 and 5, for example, right? 1, 2, 3, 4, 5, right? Now, here range queries aren't efficient because now for each value you have to go see where the offset is and then you have to go and read from the file. Correct? Now, range queries are now not that simple, right? So, in hash indexes, range queries aren't optimized, although they're better than just doing a linear search over your entire data set. Because now, when you want, let's say, keys between 1 and 5, right? You know, 1, 2, 3, 4, 5 are your keys. But now, imagine a complex scenario where now you're not searching by key. In SQL, if you have a primary key and you have multiple columns, right? Let's say you have a column status where status can be 1, 2, 3. Now you wanna get a list of all the rows where status is 3. Now that's also a range query because you need a range of values, right? So now, for these things, hash indexes aren't really optimal, correct? So hash indexes aren't really good for this. This is handled by something called B trees, which we'll look at in the next video. Okay. So so range queries not optimal on hash indexes. Okay. So to reiterate, let me come back up. Okay. For each key value, okay, we store an in-memory hash path where we say for this key, this is the byte offset where the key value is stored. So this helps us reduce the search complexity from O of n to O of 1, right? And it also comes over all the caveats that you spoke on the previous video, right? You don't have to do an exhaustive search. You know where this key is located in the particular file, and you can go to that exact location and fetch for the key valuables. Correct? Alright guys, that's it for the hash indexes. Okay. If you have any doubts at all, feel free to just leave comments below and I'll definitely try to clarify your doubts. And I'll also link my LinkedIn account below so that you can reach out to me directly and you can ask me for doubts. And I'll be more than happy to help you guys. Alright. With that said, I'll see you guys in the next video. Bye.